welcome everybody. It's a pleasure to invite you. As you can see we're here by the song. This is my hometown. I want to welcome you not only the meeting, but also the conference. Let's see if I can get this working right. So, we have today the second Emmett Award winner, and we'll talk about that. This is the slide you saw yesterday, and we have here the past awardees, including Thomas Haber, who did a phenomenal talk yesterday, and this is to honor our Emmett. And since yesterday, Marco was helping give a presentation and an introduction, an overview about the life, and so on, I thought I could focus a little more just on what Emmett really did. And there are two really groundbreaking papers when you see the years on this and what he did. So the first paper was in 1938 in Jackson American Chemical Society, where Graham, Emmett, and Teller developed a method of nitrogen absorption to determine surface area of materials. To my shock, I came across some literature that the PET equation is used more than any other equation every single day. But so many different people are measuring PET, not only catalysis, like in cement industry. They want to know how much surface area cement has and other materials. And Gunnar and Emmett were chemists who came up with the idea, and Edward Teller was a physicist, and he did the mathematical calculation of the derivation of the PET equation. Emmett and Teller both went on to work on the Manhattan Project. Beyond that, Teller also developed the hydrogen bomb in the early 50s. So he had very illustrious people involved in this. And then the other thing that was interesting, to write back to back, this is 1938, the next paper is 1940. And what did Brunner and Emmett do? They used selective chemosorption. They were trying to understand ammonia synthesis scanners, which is iron, promoter, alkali, potassium, sodium, calcium, and they developed CO2 chemosorption to count the number of basic sites, potassium, sodium, calcium. And they used CO to titrate how many metal sites were exposed. It's the real first surface characterization that I'm aware of. And it's really groundbreaking. I just want to emphasize these phenomenal accomplishments that we rely on daily in our catalysis world and research. So, I'd like to welcome Beatriz Roldan Cuenya. I said it right. And really delighted with her receiving the award. I want to say one thing. I actually studied with Emmett. Most people find that surprising. So I'm not young, but not that old. But anyway, the reason is he retired in '71, and he lived in Oregon, and I went to graduate school at Stanford University, and he used to come down for the summer to hang out with Michel Bedard and his catalysis group. And one summer when I was there, he joined teams with Jim Carver, some of you may know from chemical reaction engineering world, and they taught a course to the grad students. And so it was an old Emmett, but I actually had a catalysis course from him at that time. And I got to know him a little bit. Now, the reason I want to say is that I can tell you, had he been alive today, he would be so honored, so happy to see the phenomenal award winners that we got this year, both Tom Harvey and Beatriz Roldan Cuenya. So I'm going to invite Charlie up here, Charlie Campbell, and Charlie will do the introductions for Beatriz.
It's a pleasure and a real honor to be here to introduce the 2022 Emmett Award winner. Beatriz Roldan Cuenya is the now the director of one of the sections at the famous Fritz Haber Institute in Berlin, and also honorary professor at the Technical University of Berlin, the Freie University of Berlin, and the Ruhr University in Bochum, as well as the University of Central Florida. She received a bachelor and master's degree in physics in Spain, and went from there to get her PhD in Germany, also in physics, but not in catalysis, in the magnetic and fungi component in nanoparticles. And then she went to do a postdoc at the University of California at Santa Barbara in the chemical engineering department there with Eric McFarland. Started doing some beautiful nanoparticle catalysis work where she tuned the sizes and separations of nanoparticles of metals on support surfaces and elucidated those effects in various aspects of catalysis. She moved from that to the University of Central Florida and worked her way through the ranks, assistant, associate, and full professor there. And then she went from there to Germany and started as a professor at the University of Bochum, in the Ruhr University of Bochum in the physics department. She's been awarded many awards since then, and as I said, she's now director, one of the directors of the Fritz Soled Institute in Berlin, and directs a large group there. She's awarded the Consolidated Beta Award of the European Research Council, quite an important award. She's a member of the European Academy and associate editor of ACS Catalysis on important editorial advisory boards. And she's on the VSAC committee if you're a U.S. scientist, you know how important a role that is. But in doing all of the things that she's done, she's also been the mother of two children who are 7, I guess, years old now. And she is a surface scientist from her roots, but now does all kinds of electrocatalysis and high surface area catalysis and more traditional catalysis types of activities. I list here a few of her more important contributions in fundamental research: CO2, electroreduction, particle size, the shape and composition effects in CO2 reduction, electrocatalytic reduction, the effects of electrolytes on CO2 reduction, and the effect of nanoparticle shapes on catalytic activities and selectivities, and thermal CO2 hydrogenation on ion-atomic catalysts. And just listed some of her important contributions there. Sorry. She, as I said, was advised as a postdoc by Eric McFarland, and Eric McFarland was also the advisor for the other Emmett Award winner who we celebrated yesterday, Don Armino. And Eric is one of these super enthusiastic people, the likes of which there are many of you in the audience, that have real passion to help humanity through catalysis research and sustainable living and environmentally safer ways of having comfortable life on this planet. And I'll tell you, it's so nice to be back with this society and with all of you people, because you're a great group of people that are helping. I mean, think of how important, especially talking to the industrial people that deal with these massive amounts of chemicals and fuel processing, and how important the work is that's done by this collection of people. And they're so And you see that when you look at this list that was up there, the past awardees. These names are quite impressive. The past awardees for this award, we have many of them in the audience who are now super leaders of the field, and it should be felt as a real honor for Beatriz, my friend, to enjoy this honor. So congratulations, Beatriz.
Thank you very much for the introduction and for everybody who woke up so early today for being here. It's an honor for me to receive this award and to have this very large audience, and of course to be in this beautiful city. I will be talking about something old, something new, and something blue, and the blue is going to be water today. We had a beautiful introduction yesterday about electrochemistry, and this has made my life much easier today because I'm going to give you a little bit more in detail about what are the important things that we need to consider when we are trying to address some of the problems that we have in catalysis today. I wanted to honor first my PhD advisor, so Professor Roldan Cuenya. He was my mentor, he was my friend, and accompanied me throughout many years of my career. And unfortunately, he passed away last year. And my postdoctoral advisor, Emmett, was also mentioned, and he was key in introducing me to the field of catalysis. Actually, he was brave enough to take a physicist and try to make out of a physicist a chemist, a chemical engineer, a physical chemist. And you're going to see today how successful he might have been. And I also would like to thank the Charlie Campbell, Simon Bear, and also Jim Van Chen, who have been supporting me over the years and also nominated me and supported me for this award. I wouldn't be here if it wouldn't be for these people. These are my parents. They have been very encouraging throughout my career, and to my children were already mentioned. So these are the ones that are always waiting for me to come back from my work, and these are if you ask me about my biggest accomplishment, my twins is my biggest accomplishment to date. I woke up this morning very sad hearing about the news in the massacre in Texas, and I think, as any parent thinking about your children at the school, this should be today very sad about what happened, and I hope that this doesn't happen again. My research group at the Fritz Institute, you can see here, and a lot of the work that I will be showing today is actually the work of these people here. We have sponsors. My career, as it was mentioned by Charlie Campbell, my career was made in the US first for 12 years at the University of Central Florida and the University of California, Santa Barbara. Then I moved to Germany, and I would like to thank all the sponsors that have been contributing to my career over the years. So now let's start about the science. So we work with the small molecules, and today I'm going to be talking mainly about carbon dioxide and also water. And we try to convert them into something useful through electrocatalysis or thermal catalysis. The bulk of my talk today is going to be about electrocatalysis, but there are many of the lessons that we are going to learn today can be applied to both fields. If you are working in catalysis and you are a student or a postdoc, you have seen this many times. There is a pressure gap to bridge, there is a materials gap, and there is complexity gap. The difficulty of the field of catalysis is that in order to really comprehend what is happening in your system, you need to be able to look at your material in many different length scales. This goes from the atomic scale to the meso scale. And how do we do this? So we can spend a lot of time trying to make a beautiful catalyst, and you see here an example. This is a pre-catalyst. I always going to call it a pre-catalyst because what we make is not really what is going to be doing the catalysis. So this is what is happening during the catalysis. The material is going to be changing, and we need to have an array of techniques, and normally combining spectroscopy and microscopy, to be able to unveil the complexity of a real catalyst. And this is, if you are going from the gas phase to the liquid phase, the complication of adapting these techniques, it gets higher and higher. I want to mention that a lot of this work, especially if you are starting with a small group, a lot of this work can be done in user facilities. For example, in the US, we have the DOE supporting the synchrotron facilities. And many of the data that I will be showing today have been acquired in these user facilities that are accessible to everybody from us. So I wanted to show you the first example of how materials are changing and how to bridge the pressure gap. So we look at a material that is commonly used as a catalyst. This is high surface area platinum gamma alumina. And we wanted to see what happens to the structure of the particles when we put a lot of hydrogen on the surface. And so there was a prediction by the group of Fritz that if you increase the coverage of hydrogen or per platinum on these nanoparticles, in this case it has platinum 30, he could see a change in the shape from bipolar to cobactahedral. So you can measure these things also experimentally. So we made very well defined using colloidal chemistry, two-dimensional nanoparticles. And then we use ultrafiltering layers spectroscopy and also EXAs to look at how the structure was changing under a very large amount of hydrogen. So we went up to 21 bar of hydrogen. This measurement was done in Chicago, here at our national laboratory. And you can see that the coordination numbers is changing when we start putting more and more hydrogen in these nanoparticles, and you can go from a two-dimensional structure to a more 3D structure and then couple the particles for the support. So if we go further, we spend a lot of time over the years, as I mentioned before, trying to make a very nice catalyst, well-defined in structure, size, shape, and composition. And of course, my group has also been looking at that. But there is a problem, so I can show you that yes, we can do very beautiful structures. Some of them are synthesized electrochemically with tunable size and shapes. Some of them are used with colloidal chemistry. Some of them are standard impregnation and wetness methods. But the main problem is what happens to these catalysts under reaction conditions. Do they stay like this? And even more, does it matter the way you synthesize the catalyst in terms of influencing the activity and the selectivity and the evolution, the adaptability of the catalyst under reaction conditions? And I hope that at the end of my talk you are going to see that yes, it matters. I'm going to show you that the materials are changing, but it matters which type of structure you have to start with. So, because I showed you during this conference a lot of talks already on single atom catalysts, I wanted to start from the most simple system to the more complex systems during my talk. And we had some effort also synthesizing the single atom catalyst. And what we brought as new was some approaches to stabilize them. For example, using a plasma materials to create peroxide species on the surface and to create defects. So these are platinum single atoms on Syria, and you see here the pristine sample. This is the sample after sea oxidation at low temperature for a couple of hours at 200 Celsius, and you can see that once you do this plasma pretreatment, the catalyst is rather stable. So to show you that these are single atoms, we always combine in my group the possibility of doing basic surface science studies with doing the same work on high surface area catalysts. So I'm going to show you this, how to combine these two approaches on this example of platinum Syria. So we make very thin films of Syria or in vacuum, and then we expose them to an oxygen plasma. And you can see that you get this roughness here, you get clusters of Syria. Those clusters are going to help us to stabilize the single atoms. At the same time, if you look at Raman spectroscopy, these plasmas are also creating peroxide species, and these are also going to play a role in the initial stabilization and the dispersion of the single atoms. So working with fields is very important to be able to understand particular activity, selectivity trends, but also the stability of these type of materials. So we had a collaboration with Nuria Lopez in Barcelona, and we were looking at what are the reasons why we can stabilize these single atoms and after the plasma treatments. So we started with this Syria surface, and if you just simply put platinum on the surface and start heating, you make clusters. If you first take the same surface and expose to an oxygen plasma, you can see that you make these type of clusters. And then you also have the peroxide species. And then when you deposit the platinum in here, you can see that they disperse on the surface, and they also get attached to this and trapped into these Syria small clusters. Once you start annealing, you get rid of the peroxide species, but you still have the stabilization of the single atoms on these clusters. We can follow these very nicely using surface science methods, for example, X-ray photoelectron spectroscopy. You can see, as an example, these are the data, XPS data in vacuum after annealing at 250 Celsius. And this is the data of the platinum on the plasma-treated cilia, and you see platinum 2+, so this is typical for the single atoms, they are cationic. And you see here what happens if you put the same amount of material, platinum on the crystalline cilia, so producing metallic platinum, so these are the platinum nanoparticles at that form. So we need different treatments to the surface, and only when we have this plasma-treated surface with the small clusters and the peroxide species, we could stabilize upon an annealing vacuum the platinum 2+ single atoms. If you look at during the reaction, in this case after C oxidation at 100 Celsius, we also see that predominantly we see the stabilization of the single atoms on the plasma-treated surface. If you compare with the crystalline surface, you see here the metal nanoparticles, you also see platinum oxide clusters, and some of the single atoms remain there. So, what we learned from this system is that you could use plasma treatments on powders as well as on thin films to try to disperse and stabilize single atoms. You can use IR spectroscopy also. For everybody working on single atoms, it's very hard to prove that you really have single atoms on the surface. So you need to have microscopy, you need to have a spectroscopy, I showed you experience data. You can look at that also with IR. So you can follow, for example, the platinum CO absorption of platinum on cilia. This is without the plasma. And you see that when you deposit the platinum on cilia, you see CO with these two particular binding features. And if you do it on the single atom platinum sample, you deposit on the plasma-treated cilia, you only see one absorption site. And also this signal is much smaller than this is factor 2. And this is because you have cationic platinum species there. If you anneal this sample, you see here that the annealing at 500 Celsius gives you a very strong platinum absorption, CO absorption on platinum signal. This shows you that you have large nanoparticles, and you don't see this on the plasma-treated surface. So this is just to give you an idea about a lot of things that you can do in terms of curing the synthesis of your material. Then you need to worry about the stabilization, and of course you need to worry whether this is stable or not. So when you're starting this system, and I compare here the two versions of my catalyst, on the platinum on a planar film, and the platinum on a cilia support, and here you can see the single atoms, here you can see the roughness of the surface and the cilia oxide clusters. You do see oxidation, and you always see much higher activity for both, for the platinum and the plasma-treated cilia, as well as the cilia itself is activated when you make these small clusters. And we saw this on the thin films, we saw the same thing when we treated with plasma, oxygen plasma, with the powder samples. So stability also matters. If you do this pre-treatment and then after the first 5 minutes it works, but then it doesn't have any effect, then you can forget it. So we could see that in fact you can run for a couple of hours, we ran about 150 hours, and you see that the initial plasma pre-treatment really helped us to stabilize the catalyst, and the increasing activity in this case for non-temperature oxidation remains. Well, this was my introduction to how we can synthesize materials and how we can stabilize materials. But now I want to go into increasing the complexity of the system. So I started with the most simple system. You already see how complex it is because the single atoms are not stable by itself. You need to do something to stabilize them, and they are also not metallic. They are normally cationic. And now we can go to more in-depth characterization. And I was trying to show you here that there is a very complex array of techniques that you can use to characterize your materials. And some of them are lab-based, some of them are synchrotron-based. And it's actually the beauty of the approach is to have a combination of all of these techniques working with each other. So, for those of you in the audience, I don't think I need to introduce this, but if there are some students and postdocs, I'd like to put this slide to bring us all to the same perspective. So, for many years, we tried to characterize catalyst ex situ. So, we have the as prepared state of the catalyst, we have the catalyst of the state of the catalyst after reaction. And then we learn, this is important to look at the material like this, but there are many phenomena that we will not understand, and we cannot get complete mechanistic understanding if you are not really working under reaction conditions. In electrochemistry, for many years, people were also taking the sample and trying to freeze it and assuming that nothing's going to happen to the sample, and this is what we call here in situ. Then for some of the approaches, you need to do what we call in situ here. So you are looking at the material, but it's in a confined environment. So we don't get information about reaction kinetics, and we miss part of the reaction environment. And this is ideally what we want to do. We want to look at the material in the real environment under reaction conditions. And those of you who know me, I like to scuba dive, so you can imagine that a lot of my effort in this, in my career is to try to look at the operando environment. So I give you just an example. So we were working on CO2 hydrogenation and tried to understand the typical catalyst, copper zinc oxide catalyst. How much zinc do you really need to be able to activate this reaction? So instead of having the traditional catalyst from the industry where you have copper on a zinc oxide support, so we have copper zinc nanoparticles, and we put just a little bit, a small amount of zinc close to the copper, and we run this reaction. We look at the effect of the support, and we also look at the effect of how much zinc you have in these particles. And I put this as an example to show you that I synthesize a material like this, where when I look with HPS, and this is near the process HPS data, when I look at the concentration of copper and zinc in this material, I have initially large amount of copper on the surface and zinc subsurface. But then I go to reaction conditions in hydrogen, CO2, and CO, and also adding water, because you also could have water being produced in the reaction. And you see a very clear segregation of zinc to the surface. So the material doesn't stay as I synthesize it. And if you want to understand how the material works, you need to realize that in this case you have the zinc oxide shell that's segregated from the initially mixed copper zinc nanoparticles, that's segregated to the surface. And we did further studies on this material with also bulk sensitive techniques, and we could see that under certain reaction conditions we will also make brass, and this will be affecting also the activity and the selectivity of this material. So let's talk about the dynamic nature of catalyst. So I mentioned some gaps before, now I'm going to mention the theory versus experiment gap. So the catalyst surfaces reconstruct under operation. If you leave this room and you don't believe this, then I did a very bad job. Active sites are not static and might be created during catalysis. This is something very important because when you are trying to understand mechanistically a catalytic process, you cannot start with the modeling the pre-catalyst because this is not going to be the one that is doing the catalysis. And then you need to realize that maybe the active sites is not enough to understand the active sites, it's not enough to understand them at the atomic level. Maybe we need to look at different length scales and look at the effect of mesoscale structures. So CO2 electron reduction was already beautifully introduced yesterday, so I don't have to say much. What I want to tell you is that this is a fundamental process, aside from all the possible applications that you would have. It's a fundamental process to test what is the effect of the structure and the composition of the catalyst and also the environment in the activity and the selectivity. So we want to make some of these products. This is ethylene or ethanol. And if you look at the literature, the original work from Hori was showing that you need to go to high potentials to start making interesting products. And if you go to lower potentials, you make hydrogen. In this case, hydrogen is our parasitic reaction. So we spend a lot of time trying to understand this reaction, and this is what you are going to be seeing me presenting today, mostly. But I want to show you that there's a lot of work also in the theory, trying to find out reaction mechanism. And one of the main problems is that, for example, when you are looking at the energetic differences theoretically between, for example, let's say ethylene and ethanol, they are small. And this is a problem because most of the time experimentals were still not really able to have very good handle of what would be the reaction pathway, and detecting the reaction intermediates will be key for this. So we need to develop better analytics to be able to detect reaction intermediates, also to work hand-in-hand with theory to see what would be a possible reaction pathways, specifically for these complex reactions. And even more drastic is that when you look at the calculations that are being done for this reaction, people assume that the catalyst is static. And so we try to follow this approach and see if this is true. So we started with the most simple system that you can make, a single crystal. This is copper 100. And then we use electrochemical atomic force microscopy to follow the evolution of the surface under reaction conditions. You see here what happens when you put a perfect single crystal surface in the electrolyte, in this case potassium bicarbonate. You see this iron formation, and if you are good enough, you can get atomic resolution in the liquid, and you can see that this is copper 2O. So the surface has reconstructed when you put it under open superpotential in the electrolyte. Then you can apply the potential, we can follow this very nicely, so these are in situ studies, so we have potential control, we can follow which region we are, and we can do microscopy. And these are very difficult measurements, because when your catalyst is very active, it makes a lot of gaseous products, and if you are a microscopist in the audience, you are going to realize what this means. But we managed to image under realistic conditions, so minus 0.5 volts and minus 1 volt with respect to the reversion of hydrogen electron. And we could notice that the structure of the catalyst was changing at different applied potentials. Remember that I mentioned also that the selectivity was changing at different applied potentials, and now we have an indication that the structure is dynamic and is also changing. And you can see different reconstructions at different potentials, and these reconstructions are an indication of the interaction of adsorbates with the surface. Experimentally, we cannot tell what is the adsorbate that is causing this reconstruction. This is why we need the help of theory. Now, I told you I'm going to be increasing the complexity, so I thought that working with single crystals would be very easy, and I'm a physicist, so I like things simple. And then we realized that we will make the single crystal as perfect as possible, so we made it in UHV. We made it in ultra-high vacuum, and this was copper 111. And if you prepare like this, you can get large terraces, you can get very nice steps. This is before reaction. Then we do CO2 electron reduction for 1 hour under these conditions, and you see I destroy completely my surface. Even more, when I look at the selectivity, this surface that is supposed to make hydrocarbons was making 90% hydrogen and very little hydrocarbons. So what happens here? I follow the literature and I see that there are calculations telling me that copper 100 makes these products, copper 111 makes these products. But all of these calculations were referring to experiments that were done on electropolished surfaces. Single crystal, but electropolished. So we look at what happens when you electropolish this beautiful single crystal, and this is what it happens. You create a lot of defects. This is before reaction, this is after reaction. You can see that there is a lot of dissolution, redeposition. So the single crystal has roughness and defects once you do this electropolishing treatment. And only once you get these defects there, you start making the hydrocarbons and suppressing part of the hydrogen production. You can check why these two surfaces are different, and one of the common intermediates for CO2 electron reduction is carbon monoxide. So we look with temperature program desorption at the binding of carbon monoxide to these different initial surfaces, and you can see that on the electropolished surface you see a stronger binding of CO than on the UHV surface. So the initial state of the surface, even though it's changing, is affecting the binding of CO there, and is affecting the selectivity for this reaction. Now, if this was not enough, so we tried to see, okay, are there different active sites for making hydrogen and for making CO2 electron reduction products? And the answer is yes. First, we were surprised to see this. When we look at the activity in electrochemistry, we plot the current density, either normalized by the geometry of the sample or by the electrochemical surface area. And we did it for samples with different roughness. So this is the flattest surface, this is the highest, the roughest surface. And you can see here that the roughest surfaces were the ones that were giving us the lowest total activity. And this was surprising. The changes in the roughness here are relatively mild compared to when people are looking at three-dimensional structures. So these are all single crystals where we are introducing defects in a very controlled way. But you can learn, if you look at this into a little bit more detail, if you separate hydrogen production from the CO2 electron reduction products. So hydrogen production is shown here in red, in black. And you can see that what you are doing is, with increasing roughness, you are suppressing the hydrogen production, while the CO2 electron reduction products are not changing much. So from this type of studies, we learn that there are different active sites for making hydrogen that happens on the flat surface, highly coordinated copper, than for making CO2 electron reduction products that happens mainly on defects. So we went a little bit further and we tried to understand, can we take a surface and just prepare it in ultra-high vacuum and change the selectivity from making hydrogen to making hydrocarbons, just by controllably inducing defects? And the answer is yes. So if you look at copper 111 and we have exactly the same surface, with lead it looks the same, with STN locally the surface looks exactly the same, but we see the selectivity very different. So on this type of preparation, we see hydrogen being produced. On this preparation, we see the hydrocarbons being produced. At the atomic scale, the surface, if you look with STN, they look exactly the same. With all the surface science methods that you could possibly look, they are clean, they are preparing in ultra-high vacuum. The only difference is that this surface looks like this in the mesoscale, so you have very large terraces flat, and you have these steps here, straight. This is before reaction, this is after reaction, it's still flat. And this is the surface that makes the hydrocarbons. This is what we call a weather surface. This is when we run the reaction a couple of times, then we recover the surface in the UHV, we clean it, but it never recovers completely. You see a lot of wavy steps, and this is the surface, which at the meso scale has a lot of steps and a lot of defects. This is the surface that makes the hydrocarbons. So with this, I want to illustrate that it's not enough to look at the local scale, because locally this surface looks exactly the same. Spectroscopically they look the same, but if you look at larger scales, you see this difference, and this difference completely changes the selectivity of the surface. So I told you I'm going to increase the complexity, so you saw already single crystals. Now I'm going to take a copper surface and I'm going to electropolish it, create a lot of defects, and I hope that I can get other products that are not hydrogen, because this is what we didn't want to make in this case. And this is possible, so you can do electrochemical graphing of a copper surface, and you start seeing that you get large amounts of ethylene. You can also make ethanol. These are all the CO2 electroreduction products, so C2 plus products. And we wanted to use surface electromagnetic spectroscopy to find out which intermediates we have at each applied potentials, because we know that there is different selectivity at different applied potentials. And we focus on these two products, either ethanol versus ethylene. The onset potential for ethylene is earlier than ethanol. And you can see that the Raman spectra look clearly different when we are making these two products. And keep in mind that after a certain potential, you are making both of them simultaneously, so they could have also a common intermediate. So if we look at our Raman data, we can see that at this, and comparing with theoretical predictions, in this case also from the group of Nuria Lopez, we could see that at the onset of ethylene production, we see vibrational features in our surface ethylene Raman data that correspond to these reaction intermediates. And at the onset of ethanol, we have other reaction intermediates. And so we came up with the idea that for this particular material, we could have the same common intermediate, but depending on the characteristics of the surface, we could go from one pathway to the other, either to making ethanol or making ethylene. And what should be the characteristics of the surface that we should have? So if you look in calculations of vibrational spectroscopy data, and you look at CO absorbed on copper, you see that if CO is absorbed on copper with lower coordination number, on low coordinated copper sites, then you will have a higher CO frequency. And this you can look at in our experiments also. So if you look at the surface enhanced Raman data from this type of rough materials, we get very nice signals because they are very, very rough. And you could follow different applied potentials. And you can see that when you are making ethanol, there's this feature here that is coming up. And when you are making ethylene, there are mainly these two features here. So we can correlate the vibrational spectroscopy features with particular intermediates. And together with theory, we can find that in fact we need defects to have CC coupling. We see that when we are producing ethylene, according to theory, we have low coordinated sites of copper, in this case with coordination number between 7 and 8. When we are making ethanol, they are even more under-coordinated sites, with coordination numbers more than 7. And if you have a very flat surface, or a large coordination number, 8 or more, then we are making only hydrogen. So this is a nice correlation with the work on the single crystals. If I have a very flat surface with very little defects, I get the hydrogen selectivity. Now, if I create defects in a way where I have different coordination, and this happens also when we are applying different applied potentials, you can see with Raman spectroscopy and comparing with theory that there are different intermediates and that there are the possibility of going from one pathway of ethylene formation or ethanol formation depending on the sites that you have on your surface. So I keep increasing the complexity. I went from a single crystal to a rough surface. Now I'm going to go to nanoparticles, keeping with the theme of looking at the dynamic behavior of these particles under reaction conditions. So I can show you that we can synthesize nanoparticles electrochemically. So you see here an electrode, and I have an electrolyte with copper, and I have chlorine that is going to help me to stabilize 1,0,0 facet. I wanted to make cubic structures because there was initial theoretical predictions that on cubic structures or copper 1,0,0 we could make ethylene. I will show you that this is actually not the case because the catalysts are going to be changing under reaction conditions. So these structures you make it as a pre-catalyst, but it's not going to be stable under reaction conditions. We look with transmission electron microscopy in the liquid environment. And you see here the possibility of doing the synthesis in the transmission electron microscope, then exchanging the electrolyte, and then looking at what is happening with your material under potential control. So these are the copper oxide cubes, and this is CO2 electron reduction. We are working under these conditions, also potassium bicarbonate electrolyte, and look at the dynamics here. So I synthesize a well-defined catalyst. I synthesize what the theorist told me to make, something with 100 facets. But then under reaction conditions, I see the informational dendrites, I see the cubes break up, I see a lot of the small particles in between. And this catalyst is the one that is still making ethylene. But depending on the initial interparticle distance, and depending on the initial size of the cubes, and depending on the substrate and the interaction with the substrate, this is going to affect the stability, and it's going to affect also the product distribution. So we can look at this into more detail. So you can see also from the side here, these dendrites growing. And this is something that was very challenging. So it's hard enough to be able to look at some of these materials in the gas phase in an environmental TM. Now imagine that we're doing it in the liquid phase. Going further, we look at these cubic structures with different sizes and under different applied potentials. And you can see that this is what we synthesize. Just putting them in the electrolyte, immediately you start seeing the breaking up the cubes, the formation of these small particles. And if you leave it for longer, you start seeing the dynamics here. So this is the catalyst under electrochemical reaction conditions at this negative potential. This catalyst is making ethylene, but the productivity is also changing over time because the structure has been changing. And these changes are very fast. So the initial disruption of the cubes, so we see this is my initial catalyst, then you see the breaking up the cubes, you see these small particles forming. This happens very fast. And then you reach kind of a stable state. And this catalyst is the one that is making ethylene. Now, we try to look at whether there is an effect of the cube size, and you can see it here. So we make a smaller cubes, just putting them in the electrolyte, immediately they are detaching. They move much more, and this system is much less stable. So these are the initial cubes, putting in the electrolyte, already lost a lot of material, and then there is material redeposition. And I like to call this the dancing catalyst, because you see that this entire particle is moving, forming this type of change. So you can think these are just beautiful videos, but why is this relevant for catalysis? Does this do anything? And if you look at the selectivity of this reaction, you're going to see that this is in fact relevant. So on these larger cubes, I make ethylene, and yeah, initially there are some changes and there is some deactivation over time, but the catalyst is much more stable than when I started with these smaller cubes, and it's still very large. These are 80 nanometers. And I see all of this, the detachment, the position of the particles, and also this formation of these larger structures. So I affect the ethylene selectivity, and I start having an increase in the CO selectivity. Going back to the idea of probing intermediates, so if we want to understand what do we need to do if I want a catalyst that makes CC coupling. I told you at the beginning we need to have defects on the surface, and then the other thing is you need to have the highest CO coverage, that is one of the typical intermediates, as possible. So how can we prove this? How can we have an idea about how much CO or the CO intermediates we have on the surface? So we work with this type of cubic structure, and we look with surface information spectroscopy at the binding of CO at different applied potentials. We have this CO on copper stretching vibration, and we have this frustrated rotation CO on copper bond. And you can see that the ratio of these two peaks in the manual data changes as the applied potential changes. And at this high applied potentials is where I was making the hydrocarbons, or ethanol and ethylene. And so we found out, working with the theorist, Nuria Lopez, that when we have the maximum ratio between this peak with respect to this peak, so this binding configuration preferred with respect to this one, is when we have the maximum CO coverage on our surface. And when you have the maximum CO coverage on the surface, if you plot the Faraday efficiency versus the applied potential, you see a maximum. And if you plot the ratio of these two peaks that correlates with the maximum CO coverage on the surface, you see the same trend. So we have now a defective surface, and we have so we can favor CC coupling. Then we have the highest coverage of CO on the surface, And you can see that we have the maximum of the CC coupling and ethylene formation. And there are tricks, of course, to increase the CO coverage on the surface, so as I was shown yesterday, also adding silver, adding gold, adding any metal that will help you to produce CO from this reaction. So there is a long debate in the literature about whether the oxidation state matters, and for simple electroreduction, many people have been working on oxide-derived copper. And the question is, whether there is any oxygen remaining in this material, or what happens when you start with oxide-derived copper is that after it is becoming reduced under reaction conditions, it becomes very rough, so you have all of these defect sites that I told you that were key. So to understand this, we spent about 4 years trying to design the right experiment under operando conditions to see if there is any oxygen left in this material. Because most of the data in the literature, there are two types of groups. Some groups were saying there absolutely no oxygen, we are working under very reducing conditions, and it's impossible that you have any oxygen in these materials left. But not seeing it doesn't mean that maybe they don't have enough sensitivity in their experiments to detect it. And then there was the other group of people that were saying it's there, but they were showing just based on ex situ experiments. And of course, you take your sample out, you expose it to air, or you left a little bit of water on the surface, and it will reoxidize. So these were not the right experiments to do. So in collaboration also with the group from Robert Schnöbel, we did a very difficult photomission experiments, so random photomission experiments, in which you can look, you can put your material, in this case the copper oxide cubes, in one of these cells that are capped with graphene. And then we can do next studies under reaction conditions, under potential control. This is the same electrolyte potassium bicarbonate that I will show you until now. And what is very nice from the next data is that you can distinguish very well when you have metallic copper, when you have copper 2O, and when you have copper O. If you look at the raw data here with a further analysis, you can see that when you are working at high positive potential, you see here the clear feature from copper 2 plus, and you see also copper plus. You start the reaction, you go to minus 0.1 volt, and you start seeing here that the copper 2 plus is gone. You still see copper plus. But now I'm here under my negative electroreduction conditions, where I'm making ethylene and the hydrocarbons, and look at this laser spectrum. Anybody can look by eye that this doesn't look like metallic copper. And so what we believe that we have here is some oxygen left over in the copper. And this mix of copper metallic sites and some oxygen in these structures is actually favorable for the hydrocarbon production, in particular ethanol. I will elaborate a little bit more on that in the next part. So it's very difficult to get this intermix of metallic species and maybe copper plus species. We are working under very reducing conditions, so we thought maybe we can increase the dynamic behavior of our catalyst. I show you that just under constant potential, the catalyst is very dynamic. Now I'm going to try to drive my system farther from equilibrium, so I'm going to force it into states that otherwise you will not get under potential static conditions. So we wanted to achieve something like this. We wanted to apply potential pulses and go to an oxidative regime. So this is the potential at which we do CO2 electroreduction, and this anodic potential we can oxidize the surface. So we know at which potentials we need to go to oxidize the copper surface, and this is what I wanted to reach. I wanted to reach something that will have an intermix between maybe cationic copper species, maybe some oxygen dissolved in this material, and then in contact with metallic species. And this is possible. And then we wanted to look at something else. What happens? Can we tune the selectivity on purpose if we increase or decrease the length of the anodic pulse or the length of the cathodic pulse? So again, I'm taking my system further away from equilibrium. I'm forcing it to oxidize, and then I'm running the reaction under these very negative reducing conditions. So if you look at the selectivity, from this complex plot, you can focus on this. This is ethanol. This is one of the most difficult products to make. And you see here in this area that for a certain length of the cathodic pulse, this one here, and for a certain length of the anodic pulse, we can get an increase in the ethanol production. So if you only did electrochemistry, you can see this type of diagrams. You say very well. So there is certain potential pulses giving an increase of ethanol. And the question is why? What happened to my material under these conditions? So we can go and look at this very carefully. And this is again when it comes to synchrotron characterization. It's very important. There are major developments in the latest years. Also being able to look at your materials very fast, and very fast in these cases is getting a spectral actually, for example, with operando con extraction spectroscopy with sub-second resolution in these electrochemical cells, or also with operando high-energy X-ray diffraction. So I'm going to compare the two methods. I always ask you about this complementarity. I mentioned this complementarity. Why it's important to have the two methods together. With XRD, I get information about the order phases. With XRD, I get information about anything, so order and disorder phases. And the two of them together allow me to follow my catalyst under these dynamic conditions with sub-second resolution. So you can see here, I'm applying these pulses. I see that how the current is changing. I can record how my metallic copper component is changing following the pulses. I can see the oxidation of my material. In this case, this is copper 1 species. This is all from the XR data, in this case says, quick. And then I look at XRD, and I can also see, for example, how the coherent is following also the pulses. I can see also the change in the peak intensity. And this gives us very powerful information about the structure and the composition of the catalyst during the catalytic performance. So looking at a little bit in more detail, so you see here the local structure with extraction spectroscopy. You see the change in the current very fast. The oxidation happens slowly during the pulse, and the reduction is happening very fast when I change the pulse to the reducing conditions. And I can follow whether I have copper 1 species, copper 2 species. If I go now to the XRD, I can look at the same, I can look at the peak area, I can look at the coherent length, and I can look at the strain. And within a given pulse, I can follow the evolution of the strain also for different planes. So these are very difficult experiments to do, but I think they contain a lot of information. So we see the quick reduction of the material under the cathodic pulses, the slow reoxidation, and from all of this data combined with electrochemistry, we can find out what is the structure of the material and what is the composition of the material while I'm making ethylene or while I'm making ethanol. That's what we wanted to figure out. And so we came up with this explanation. So our most difficult product to make, ethanol, happens when we have a combination of metallic, copper on the surface, and also disorder, copper 1, copper 2 species. So this is the catalyst that is making ethanol. If you work with oxidizing pulses, that gives rise to a very thick oxide, so you have a bulk, XRD detectable copper oxide, then you don't make ethanol anymore, you start making CO and methane. And on the metallic surface, the effective metallic surface, you are making the ethylene. So we can do this type of studies and realize the complex interplay between reversible oxidation, reversible oxide formation, and the catalytic function. We know now what we need to have to favor the ethanol production. And we also know there was a discussion in the literature, is it good to have oxides or not? It depends. If you make a bulk oxide, then this is bad. You don't favor CC coupling on a bulk oxide. But if you have this mix of a highly disordered mixed oxide and metallic, then you get products like oxygenates. The last part of my talk, in the last couple of minutes, is just to show you the same things, the same approach can be used to get understanding of water splitting. So the most difficult part of water splitting is understanding the oxygen evolution reaction. And I chose just an example from very recent data to demonstrate that the complexity of looking at a very simple catalyst. So we made a very simple catalyst. We made cobalt oxide particles, very well defined, with different sizes. And we wanted to see, is it enough, as many people are doing in the literature, they are showing the data before the reaction, they are showing us the data after the reaction. And do they really have information about the active state of the sample, or is there much more complexity there? So we can see that with decreasing particle size, when we go to these 1 nanometer particle sizes, the activity, in this case, either mass normalized or also area normalized, the specific activity, we see that they're both increasing when we go to the small particle sizes. Now, we look with the extraction spectroscopy at our smallest catalyst, in this case these were 1 nanometer particles, in their prepared state. And you can see that once we go to the activation of the treatment, the activation treatment there is going to a 1 volt potential with respect to IHE, and we do 20 cycles as indicated here. So you can see that there's a very clear change, so there is a shift in the sales spectrum here. Then you go to the OER conditions. The OER is done at, in this case, at 1.7 volt with respect to IHE, and you see a further shift. And once you stop the OER and you go back to the activation state at 1 volt, you see that it's reversibly going back. But this is the active catalyst state, the new one. And you can see that it's not, you cannot find out what is the active state if you only look at the as prepared catalyst or the after reaction catalyst. This is a different state. So we can follow this with extras, and we are going to be looking at the cobalt-oxygen bond lengths and how they are changing under reaction conditions. We're also going to be following the oxidation state, and you can see here, for different particle sizes and different reaction conditions, how is the oxidation state apparently changing. You can see that when you go to the smallest particles, you see the highest increase in the oxidation state under potential control during OER. So, very important, if I look at the activated catalyst before or after reaction, I don't get really the state of the catalyst under reaction conditions. It's changing and it's reversibly changing. So, you see here an oxidation state of 3 point something, 3.2 or so. And there's a strong debate in the literature for iron, for iridium oxide, and also in this case cobalt oxide, whether the reactivity or the active state of this type of OER catalyst is really when the catalyst is in a high oxidation state. So in this case, more than 3+, 4+ or so. And I want to illustrate here that this is not the case, that there are some things that are missing, and we simply think that everything that is happening here is that there is an apparent high oxidation state of cobalt. What is in reality happening is that on these smallest particles of 1 nanometer or smaller, there is charge distribution and there is charge extracted from the oxygen, and I'm going to show you that we make this oxygen. And this is here what is giving us the impression that we have high oxidation state. So how do we look at this? So we look at experimental data and we look at the cobalt-oxygen bond length, and we see the change of the cobalt-oxygen bond length, and we look at the change in the cobalt oxidation state. The reference in orange are typical compounds with either cobalt 2+ oxidation state or cobalt 3+ oxidation state. The blue one are the experimental data under OER conditions for the different particle sizes, and here in yellow, these are the data of the as prepared particles. You can see there are 2 clear regions there. So when you look at So when you look at this, in this range here, you see the cobalt 2+ oxidation state. Here is the cobalt 3+ oxidation state. And you can see that in the cobalt 2+ rich regime, there is a strong change in the cobalt oxygen bond length per extracted electron. Here, there is, in the cobalt 3+ regime, there is a weak change in the cobalt oxygen bond length per extracted electron. And the question is, how does the particle size affects the cobalt oxygen chemical state in the OER? So we can look at this here by looking at the decreasing particle size. We can look at the increase in the oxidation state, and we can see also this is the contraction of the cobalt oxygen bond, and we can see also an increase in the cobalt oxygen in the contraction of the cobalt oxygen bond. We can extrapolate to the near surface regime, and then we can get this type of cobalt oxygen 6 delta plus structure that would be the proxy for our surface state. If you look further, you see here the same data that I showed you before. This is the change in the cobalt oxygen bond length, this is the change in the oxidation state. This is our active catalyst. These are for all the particle sizes down to 1 nanometer, and this is here the extrapolation when we go to the near surface. We work with physics to try to see, under these conditions, what do we really have in our catalyst. So Travis Jones from the Fritz Institute in Robert F. Lewis' department did calculations for us, looking at different cast structures here. And it looks like the one that better fits the experimental data is this oxygen determination. So what we learn from our studies combining operando extras with DFT is that actually we have this oxide formation during OER, and that there is no high-value metal ions driving the OER for this type of catalyst. And we believe that this is general also for iridium oxide catalyst and other similar OER catalysts. So with this, I will come to the last part of my talk, so my take-home messages. I hope that I can show you that the synthesized materials are only pre-catalysts. They are not stable and they adapt to the reaction environment. So they make bonds, they break bonds, but this is actually not your real catalyst. So the changes in the pre-catalyst and the working conditions are part of the dynamic operation and the dynamic performance of this catalyst. And it is unclear a priori if these changes are going to lead to activation or deactivation. That's what we still need to do the experiments. It's a challenge to unveil the real structure of catalyst and under reaction conditions. And what you really know is that it's certainly different from the pre-catalyst that you need. However, the initial structure of the pre-catalyst influences the way it adapts and the way it transforms under reaction conditions. So it is still important to be able to synthesize the catalyst in a particular way, because the initial structural composition of the catalyst is going to affect whether it's able to adapt and how it's going to adapt and how it's going to be changing under reaction conditions. And this, of course, affects the selectivity and the activity. In order to get understanding on a catalytic process, we need to get the traditional prenatal post-mortem analysis of the catalyst, but this is not enough. I hope that at the end I showed you this data on the water splitting catalyst, showing you that the active state of the catalyst is formed under reaction conditions, and that you really need operando characterization to understand what is doing the catalysis there. And the last part that I wanted to mention is that we need a strongly theoretical approaches that can better describe the dynamics of this material. So how the material reconstructs under reaction conditions, and how does it adapt to the environment. This cartoon just represents the summary of my talk. So we have a pre-catalyst, and if you only live with one technique, you really don't get the complexity of this material. Then we apply the technique characterization. We also see that the material has changed under reaction conditions. And then, quoting Einstein, so we need to, in this field, it's very important to follow this approach. We need to make everything as simple as possible, but not simpler. And this means that if you are trying to synthesize and do materials, do design of materials, you cannot forget that what you synthesize is not actually what is going to reveal the catalysis, and you cannot obviate the environment. With this, I will close my talk, thanking my research department, the Fritz Institute, and also the collaborators over the years and at different light sources in the US and also in Europe and elsewhere. And thank you to the board committee for this honor, and I hope that I could give you some take-home messages and keep you entertained.